So if I go to the
on the home page.
Yeah, I can also see it as soon as I open it.
Yeah, it works for me as well.
If I open it in incognito mode, it works. If I open it in a regular browser, it doesn't. So I don't know.
Interesting. Hi, Guillaume. Hi, Renee. Welcome. Hi, Scott. So for information for the team here, Scott Wilson was one of the students in the Helen Carswell program that was the inspiration for the mission that you're about to present. So So I'll give it another couple of minutes and get a few more people in. I think the YouTube link approach that you've got works well, thanks. So, hi, Lucas.
Hey, Franz, how are you?
Yep, very well. Good to see you.
Good to see you too.
So to those of you who've just joined, welcome. So we have Ian. Hi, Ian. Hi, Andrea. Hi, Theo. We will be starting fairly soon. We're just going to give it a couple more minutes for a couple more people to show up. And then we will get going. For information, for those of you who are joining, we are streaming the presentation on YouTube. There is a YouTube link that we'll be streaming to. So if you're uncomfortable being on camera or saying things out loud on something that's going out to YouTube, do feel free to use the chat. When we finish the presentation, we will have the Q&A session without the stream. So if you have questions, then you can feel free to dive into those. But we will have questions during the presentation, which will also be part of the live stream. So just to let you know, that's going to happen. And it is 101. We have a good number of people who've shown up. We'll give it another couple of minutes just to get a couple more people in, and then we'll get going.
Good afternoon, Franz.
Hi, Stephen. Thanks for joining us.
It's a pleasure, mate. I love it. It's a delight. I mean, forgive me if I'm out of place here, or it was just lovely to pop in and say hi or anything like this.
No, it's wonderful to have you, and perhaps you just want to say who you are to the rest of the team, because
Yeah, of course.
they know your daughter, but they don't necessarily know you. So.
Of course I am. I'm Steve Alsop. I'm a professor in the Faculty of Education, and also I work with engineering, but I also work with sciences as well. And my area is primarily sort of science and education. I combine the two together. I had my first degrees in physics, my kind of second degrees in education, and then I have a philosophy in a doctorate in philosophy of science with a focus on education. So that's kind of where I am. But most importantly, and most significantly, I am Olivia's dad. And so, I mean, all of that, I think everything that I've done is insignificant other than the last piece, which it's lovely to be here and to meet you all. And I mean, I've kind of talked to Olivia, and it's a little bit, and it's just such a really beautiful and powerful initiative. I mean, and the idea of learner-centered, the idea of focusing on water, the idea of focusing on Indigenous communities and looking at this is so powerful and so innovative, and it's just lovely to be part of it, and lovely just to drop in and really just to celebrate with you this course and also what I'm going to listen to, not in a critical way, but in a way that I'm just really lovely, excited and energized to be here. So please, you know, I'm not going to ask lots of hard questions or do any of those things. It's just lovely to be here as a way of celebrating. So, Franz, I hope that wasn't too much, and forgive me if I talked for a little bit too long, but it's lovely to be here.
No, that was actually a wonderful introduction to the afternoon, I think. So thank you ever so much, Stephen, for that impromptu introduction to the afternoon. And on that note, I will very happily pass over to Celeste to get us started. And Haya, are you going to share screen again, or whoever's sharing screen, go for it.
Let me know if you can see my screen.
Okay, I think I have access to everything now. So let's just jump into it. I'm Celeste Kalura. I just would like to thank everybody for coming to our mission concept review today. Very excited to have you here. So our mission aim is water, meaning water accessibility testing and equity rapport. We hope to provide communities in Canada that struggle with access to clean water with information about the contaminants and the state of their water. Can't quite flip the page. Sorry about that. I went a little too far now. Very sorry.
Always happens at the beginning.
It really does. There we go. So before we begin, even though we are not currently on York University campus, it is extremely important for us to acknowledge the land that York University resides on. So York University recognizes that many Indigenous nations have long-standing relationships with the territories upon which York University campuses are located that precede the establishment of York University. York University acknowledges its presence on the traditional territory of many Indigenous nations. I also encourage everybody to take a look at the website native-land.ca to see the lands that you're all currently on right now. I would also like to acknowledge everyone that has been able to help us over these past few weeks, and those of you who are attending today. Without you, we would not have been able to get this far and be able to even present to you today. So our team consists of 18 students from a range of different programs, not only in space engineering, and then we also have a couple members from our admin team. So a little bit about us. Our team is divided into 5 groups. We have program management, systems design, mission design, impact, and communications. Each member has a designated group, but everyone still has an opportunity to work with the other groups and still gain experience in the other subgroups. So this is a unique student-run pilot program. It's led and overseen by Associate Professor and Undergraduate Program Director for Space Engineering, Franz Newland. In the pilot program, we want to challenge the traditional classroom experiences, and we want to show the difference for the better that project-based engineering can make. Many students feel that the work that we do in a traditional classroom setting will not prepare them for when they do need to get into the workforce. And this pilot is meant to show that this type of project-based learning is feasible. So over these past 6 weeks, they were used to design the plan to develop the mission in 3 years, then operate for a year in a 4-year undergraduate degree. There's not a guarantee that this program will even run. We're hoping to see that it will run. What we're doing is just to see that it would be feasible or useful. But as of right now, we're not going to be following through with this mission and building a satellite. It's just a trial run to see if we could even do it in the future. So I'm going to hand it off. Very sorry. I'm going to hand it off to Daniel now, and he will talk about the water problem in which we wish to address.
Hi, I'm Daniel. Thank you very much, Celeste. And yeah, I'm going to talk quickly about the water problem that we're actually going to be trying to address in this mission concept. Yeah, so currently in Canada, we have 835 water advisories around us in our backyards throughout, everywhere. You can see it on the map there, all the different places. Those are all different water advisories. The issue is right now we have 58 long-term water advisories on top of the as part of the other ones. And these water advisories can affect a lot of things, such as like bathing, cooking, cleaning. The water might smell funny. If you take a shower, you might have to close your eyes, make sure you don't get it in your eyes or mouth or anything like that. And if they don't boil the water properly, they can get flu-like symptoms, such as like diarrhea, a fever, and just a bunch of unpleasant things. And the reserves currently fall under the jurisdiction of the federal government. So that means a lot of the water data that's collected is usually collected at the source, and it's not actually collected to the household. And the Neskantaga First Nation has been on a long-term boil advisory since 1995, and that's just unacceptable. We can't let these issues persist any longer. So I'm going to hand it back to Celeste.
Thank you, Daniel. So as we heard, these are issues that need to be addressed right away. And with this mission, it will provide these communities with these water quality measurements and empower them with the knowledge of the contaminants in their water. There's this long-standing mistrust between the Canadian government and these communities. And by giving them access to this knowledge, it can help them feel more in control and give them power of information. This mission extends even beyond just measuring water quality. We have a secondary mission to provide communication service through an SMS, and there will be an ability to send out emergency messages. With missions like these, it opens up an opportunity for collaboration, and we want all our decision-making to be transparent, as well as opening up opportunities to support communities worldwide. We've worked with students from the Federal University of Pernambuco in Brazil, and if a mission like this were to run, it can provide water quality information there as well. So the purpose of our MCR is basically to show our preliminary concepts for this mission, and we want to express why we believe the mission is feasible, and we hope to receive feedback from you, and just so we can adjust our thinking where we would need it. So we provided you with an email package, and in there were some key questions and points that we would like you all to keep in mind throughout this presentation. And we will have those question periods at the end. And these are just some key points that we would hope y'all could keep in mind during the course of this presentation. And right now I will be passing it on to Amal to explain the concept of operations.
So, so coming on to the concept of operations, the water, my name is Amal Dev, so I'm part of the missions team. So I'll be explaining the concept of operations here. The water mission will have the typical phase of operations of a CubeSat, such as the launch and early operations, commissioning, routine operations, and end-of-life disposal activities. Here, we'll be primarily discussing the routine operations, which has two distinct operating modes. They are the normal and high priority modes. So the picture we are looking at right now shows the concept of operations for the high priority water quality operation. Starting from the left, the CubeSat initially communicates with the ground sensor suit placed in the vicinity of the water body. The spacecraft will transmit a signal to the sensors using the communication system. The sensor suit receives this beacon and uplink the water quality data. This data can include the concentration of contaminants, the turbidity of the water body, and etc. The satellite stores this data until it passes over the ground station. It is worth to note that the data is kept as is on the spacecraft. At this point, a link is made between the ground station and the satellite. What does link mean? It simply means that a connection of the communication systems is made. From here, the satellite sends down the raw data from the sensor suit to the ground station for processing, as well as the telemetry data. Here, the telemetry data simply means the data within the spacecraft data within the spacecraft that is concerned with the battery health, power, etc. The ground station then sends up commands to the spacecraft, which can be a software upgrade, disk cleanup, or onboard computer reset. Along with this, the high priority alert data is sent. What does this mean? Well, we have talked about the spacecraft sending the raw data to the ground station. Then it is processed. This processing compares the measured values with a predetermined standard and determines if there's a severe contamination or other emergency. In the case of a high priority alert, the spacecraft sends a message just like our Amber Alert system to every SMS devices. So in this picture, we show the concept of operations for the SMS. This one is a normal priority operating mode. From the left, the user sends a message using the SMS-like device. It is worth emphasizing the word SMS-like because in a normal SMS system, the users send and receive almost instantaneously. Here, it will take a lazy amount of time for the satellite to reach in the vicinity of the receiving user device, and maybe even more if a link cannot be made. Each message is stored for 60 days, starting from the receiving time, after which it is removed from the storage, and the SMS is transmitted to the end user. So this is the high priority SMS alert concept of operations. And this concept is fundamentally similar to the water quality alert we discussed, with the exception of the ground station. Here, the user sends a message as an emergency, which is stored in the CubeSat and then broadcasted just like the Amber Alert system. It is also worth noting that these alerts will only be received by the SMS terminals designed to receive the alerts. And that's all for the concept of operations. Now I will pass on to the impact team.
Thank you, Amal. Sorry, trying to go back here. There we go. Okay, sorry. So hello, everybody. I'm Derek, and I was a part of the team that was looking at the impact assessment. So in this section, we want to be talking about the impact assessment side of the 6-week pilot. We'll talk about how these assessments affected the decisions that we made for this mission. as well as the role that we see it playing in the 160-week program. So the overall purpose of our impact assessment was to analyze the various social, environmental, political, and economic impacts that this mission could create, and also to figure out ways of better determining the relative impact of each. So this is a bit of a tough task, and it's usually approached in the traditional engineering design sense by making some sort of quantifying framework so we could put impacts on a scale from better to worse. We instead approach the problem with the fundamental assumption that there's no such thing as a value neutral engineering project, which also means that there's no single scale that we could put these complex impacts on to rate it from better to worse. Essentially, every decision that we make is a statement of value. And rather than attempt to shroud that fact through some process of quantifying impact, we wanted to embrace that subjectivity. And we instead aim to create a process where the differing viewpoints are invited to give us feedback and criticism. So with this assumption at the core, we also had several other factors we wanted to keep in mind. So we wanted to ensure that we uphold equity amongst both community members and the design team. We wanted to provide a platform where all voices could be heard and valued. We wanted to ensure that we act in a way that is promoting the team charter of values. And in summary, what we really want to do is incorporate empathy into every step of the design process. So to overview, this is our process. It looks a little complex, but we will walk through it. But to begin, what we really wanted to do was make a process rather than a framework. So in this way, it's not just based on the assumptions and viewpoints of the people that made it, but it also allows us to incorporate the views of everybody else who participates as the program proceeds. So we'll walk through an example. The process always begins by defining an action. So this could be a mission or program decision, it could be a trade study, point design, or a part and manufacturer selection. Now, not all impacts are relevant in all cases, so they'll be selected and justified before beginning. So for example, if we were deciding on a launch provider, we may want to consider the social, environmental, and political impacts, but the technological or participant impacts may not be as essential. So next, what we want to do is assess each relevant impact. So we wanted to approach each individual impact with at least 2 distinct methods, the results of which could be compared with one another, and our assumption being that the similarities would likely be good representations of the impact, whereas the differences would allow for discussions on the methods themselves, which would hopefully lead to us improving them as the program progresses. So once the methods have been applied, we want to summarize our findings. So this summary would include the decision that we made, as well as the data and the reasoning that we used to get there. This information would be captured all by one document, which would make it easy to both distribute and to critique. And this critique process is the most essential part of this impact assessment process. So this point allows us to revisit our decision-making process, assessment methods, and the overall impact process itself. So we'll take a bit of a closer look at that process now. So in the context of the 160-week program, we imagine that this would be a weekly cycle where the impact team is providing their assessments, and over the next week, it would be critiqued and returned to them so they can make the necessary changes. Most of the critique would come from members of other sub-teams, and in that way, they would always be encouraged to be thinking about the impact of their decisions, even when they're not directly in the impact team. They will, the members of the other sub-teams would critique it either from their own point of view or through the point of view of one of the personas that we would be developing at the start of the program. As you can see, we will also be inviting outside expertise to critique our methods. This will be especially useful when using methods that the team is less familiar with, such as the environmental impact methods that we have. Or, such as in the case of social impacts, members of the community themselves will be invited to give both feedback and criticism. In year 4 of the program, we will also be able to compare the predicted impacts with the actual outcomes. And this will give us a chance to review the overall impact assessment process and make the necessary changes for the next iteration of the 160-week program. So overall, this critique allows for a diverse range of voices to be heard and responded to. And it also prevents the design team from becoming sort of an echo chamber. So now we're going to take a look at some of the impact assessment methods in detail. So the first is the social impact. So to be clear, this section refers to the impact on members of the community, which will be directly affected by the mission. Now, this section has also had by far the most thought put into it over the 6-week pilot, because we thought that it was the most important thing to get right. So first, we want to begin with a learning and an unlearning process. So when this team started looking at the way to assess impact, we started by thinking of ways to translate human sentiment into some sort of numerical system. You know, add it all up, choose the option with the highest number, and that's the best choice. But after speaking with many different people with a diverse range of worldviews, we realized that we had it somewhat backwards. And it's not necessarily up to translate human need into design goals, but it is up to us to shape the design process to fit human need. So it's a big shift in the way that we thought about the process, and one that we knew would be necessary to have in the beginning of the program before people started determining the impacts of the mission. So for the purposes of the 160-week program, we would want to recreate this process by inviting many diverse speakers for presentations and workshops before the team starts thinking about impact. So once that's complete, we would begin establishing a mode of communication between ourselves and the communities we're working with. We would likely start this process through organizations who are already in contact with the communities we want to work with. And then we would hopefully reach out to the community leadership. So once established, we would begin conversations with the communities to build relationships and figure out how we can best collaborate to reach a solution that works for the community. All of our assessments, again, and summaries will be open to the community. And there will be some specific assessments where we would invite the responses just to make sure that we are on the same track every step of the way. For the social impact, we would also want to perform a sustainable development goal analysis. So we would begin by looking at the goals and indicators which are relevant to social impact, and then looking at how to best measure those indications. We can compare and contrast these methods and gain more insight into the actual social impacts. Now, keep in mind that this method will need more work at the beginning of the 160-week program, as it's not fully completed yet. I will now pass it off to Krishnika to talk about the environmental impacts.
Thanks, Derek. Hi, I'm Krishnika, and I will be going over the environmental and the participant impact of this mission. So the environmental impact is one important impact that is difficult to design for, simply because of the number of ways the environment is affected by our activities. So in order to analyze the environmental impacts, we made use of two different methods. The first one is we went over the United Nations Sustainable Development Goals. And the second method was the life cycle analysis. So for the United Nations Sustainable Development Goals, out of the 17 goals, we were able to narrow down 4 of the most important and relevant goals that were related to our mission. We analyzed the targets and indicators of each of these goals and summarized which one of these targets and indicators are related to our mission. And then using that, we created a framework to work on the analysis for the environmental impacts. Also, throughout this process, we kept in mind that some of these goals are maybe directly or indirectly related to the environment. By using the UN Sustainable Development Goals, we aim to track down the effects this might have on the community as a whole. And then for the life cycle analysis, this focuses on the raw material that is produced and the impacts on the environment this process might have. For example, extracting raw materials might pose a threat to the land area surrounding and might indirectly affect the habitat. This analysis focuses on a particular product or material. It looks at a product at every step of its production, from when it comes out of the ground as a raw resource to the time it's disposed of, including the amount of waste material that is produced. And every step along the way has a material and energy inputs and outputs. And by estimating these inputs and outputs will allow us to approximate the total energy and material cost of the product. Also, we also have to keep in mind that both of these methods will need further exploration during the full 160-week project, and we would like experts to critique our first couple attempts at it. The critiques of this particular process will hopefully lead to better methods for determining environmental impacts. So the other important impact we were able to analyze was the participant impact. So the participants here refers to the members of the design team. In order to analyze the participant impact, we looked at two different categories. The first one is the impact that the mission has on the participants, and the second one is the educational evaluation. So the impact the mission has on participants. This includes decisions made during the mission planning, which will affect participants. In order to analyze the participant impact, we are planning to use some surveys, self-assessment, or self-reflection tools that will allow participants to track their own personal growth and impacts on their self-improvement. So one self-assessment tool we've been using is the ITP Metrics. So ITP Metrics is an online self-assessment tool that allows students to give feedback to other team members. It has a set of questions that allows us to reflect on the performance of each team members and provide suggestions for improvements. And we believe that by using ITP Metrics, it will ensure that each team member gets a chance to improve themselves based on the feedback they receive from the other team members. And for the educational evaluation process, we kept in mind that this is completely an educational experience, and we also recognize that self-assessment is not a good enough tool for evaluating educational growth. So in order to evaluate the participant and the educational impact, we plan on having a panel of professors, experts, academics, community members, as well as members from the team itself to create the rubric against which the participants will be evaluated. In this way, this will ensure that the engineering needs of the community are captured by the rubric, and this will also ensure that we adhere to the team charter values and that we uphold the engineering design principles and ethics. In addition to that, this rubric may also be subject to the accreditation board's approval, as we would like this program to provide an accredited engineering degree. So now I'll pass it over to Derek.
Excellent. Thank you, Krishnika. So there are several other important impacts that we have not had a time to look at in detail over the 6-week pilot. These include political, economic, and technological impacts. Now, these methods the methods used to assess these impacts will be a focus at the beginning of the 160-week program. So we also came up with some requirements. So for the purpose of this pilot, we examined some of the impacts that the mission may have, both socially and on us, the participants. From this, we created a list of requirements, which can be found in the requirement document. But here in this slide, we have chosen 5 of the most representative or impactful requirements. The first is that communities shall determine the desired goals and outcomes of the mission. The second is that the design team shall be the deciding factor on what is feasible for the mission scope. So these 2 requirements go hand in hand because we want the communities to be telling us what they need, where we are there to manage budgets and also to make sure that expectations are managed. The third requirement is that the design team shall reflect on their bias and assumptions about the desires of the community. So we know that it's not possible to set a requirement to remove bias and assumptions, but at least if we can find a way to make ourselves cognizant of it, we can watch ourselves and each other when those biases and assumptions start to creep in and guide the way that we're doing our design. The fourth requirement is that it shall be ensured that when community members are consulted, they are compensated in a way that they deem equitable. This comes back to our team charter values of respect. And it also, we really wanted to make sure that all members of the communities know that their voices are valuable and we want to be hearing them. And the fifth requirement is that the design team shall ensure that work which is done in the community is performed by members of the community, unless otherwise indicated. So this is really to ensure that we are not taking educational or economic opportunities away from the community through our project. So now I'm going to pass it off to Celeste to speak more in detail about the communication.
Doesn't want to ever work with me, does it? There we go. So a big way to have a positive impact is ensuring that communication is key when you're working with different groups and people. So our communication needs to cover outreach to the communities, the general public, as well as inter-team communication. Within a team, it's important to know what every group is working on and keeping everyone up to date with the group's progress. So what we do is we send out newsletters. It's a fun way to make sure everybody knows what's going on and which tasks have been completed. And it's also just a little bit of entertainment. When we outreach to these communities, there are a few steps that we need to go through. So that is training, which needs to be done before we even go and speak to these communities. We need to establish bonds once we initially meet up with these communities, and a presentation needs to be done to ensure that all parties are aware and understand the mission that we hope to achieve together. So following Canadian and York University guidelines before any outreach is made to the communities at all, ethical training must be completed by every member involved in the mission, because all members will at one point be working with these communities, and they need to undergo this training to know how to approach a situation. So in order to be even granted approval by the York University Office of Research Ethics, the TCPS2 training needs to be done. And this is a training that goes over the ethical conduct for research involving humans. Even training that is not mandatory will be completed. We'll look over the First Nations Ethics Guide, as well as reviewing Canada's plan to support Indigenous research and research training. So once the training is complete and the team members feel confident, then the outreach may begin. The communities to be approached will be chosen based off of the based off of the impact requirements, and it will only be finalized through consultation and agreement with these communities. This would include looking at a variety of possible communities and understanding their specific water-related issues, boil advisories, if they have like hydroelectric dams, any mining or fishing and hunting contamination. And it's important to remember that when we're working with these communities, that every community is different. There is no one-size-fits-all solution, and many approaches and iterations will need to be made. So initial contact with key representatives and council shall be made before even speaking to the rest of the community, and a presentation should be made to explain the mission, how the goal is to help while working alongside the communities and ensuring their needs and concerns are met. It's meant to be a partnership, and the community members know what's best for their communities, and that will be a crucial component in tackling the issues. So this bond needs to be created between the community representatives and the communications team before the mission can even begin. And when presenting the mission, the members need to ensure that the information they're presenting is understood. So this is avoiding the use of overly technical knowledge and maintaining just a constant understanding between each other. And only once the council representatives hears the idea and approves of it can it be presented to the general population, and accepting ideas where they are most beneficial. So for the presentation, this would again address the mission and the needs that we wish to address and further explain the collaboration. This will be done to the overall communities once we get that approval from the community representatives, and we'll have models to demonstrate and clearly explain what we hope to do and what we hope to have like working with each other as a collaborative group, and how we want them to be involved. So now I'm going to pass it off to Michelle to address the outreach to the general public.
Thank you, Celeste. So in addition to having a plan to reach out to these communities, we have already started reaching out to the general audience. We use three main ways. That was website, articles, and social media. And we were at an advantage because of COVID. Most people were at home, so it made it easier to reach out to them. So for the website, we wanted to create a public platform where people could interact with our mission, learn about what we want to achieve, have access to our documents like the team charter or the requirements document and the mission concept report, and also be able to provide us with any feedback that they have, or pose any questions from our feedback and contact us page. So it was just a way to reach out to them where they could be involved with our mission. The second one was we used an introduction. We made an introduction article that was posted to the Lassonde website and their various social media platforms to get as much traction as possible for our project. It was a way for us to reflect upon our challenges or what went well, so that it develops, strengthens and develops our 160-week program. And apart from these three main ways of engaging with the audience, we also had a lot of word of mouth. It was, it was a great means of communication where you just have a conversation with your friends or family and tell them to go read the article or go visit the website or be part of the YouTube live stream that is going on right now. So we just wanted as many colleagues and students to be part of what we're doing and get involved as much as possible. So to summarize the impact and communication section of this MCR, I will pass it on to Derek.
Thank you, Michelle. So just to summarize what we've heard so far, we want to design with empathy. We want to allow room for critique, listen to all voices, diversify our methods of analysis, and collaborate at every step. We can now open the floor for questions if people have so far.
And just to be clear, this is really a space for clarifying questions around the impact section of the work that the team's done. We'll be moving on to the other sections after this. We just wanted to leave a space for anybody who had questions on how the impact aspects and the communications aspects of the work that have been proposed have come together. Any questions or comments? If not, then I think we can move straight on.
Hi, my name is Ryan. I'm Mission Design Team.
It's muted again, Ryan.
Okay, does that work? Hi, my name is Ryan. I'm Mission Design Team Lead. So the main requirements for the actual mission itself, the high level requirements that we've created, this is a summary of them. The first one is the mission shall provide regional water quality data to predominantly indigenous communities, especially in the northern areas. Data shall be processed into a format that allows for a configurable data reporting. So a spreadsheet would be useful for that, allowing just the communities to determine how they want to display their own data and spread the data if needed. The mission shall provide a simple messaging service, simple messaging and alert service to communities. The mission shall provide alerts when concentration of contaminants exceeds configurable parameters. That allows them to have control over what they want to consider an alert, what they consider a risk, because we don't want them to have to go by our guidelines. We can provide recommendations, but we want them to have the control over it. The satellite shall collect data from all sensors at least once every 24 hours. This will ensure that all data is kept up to date and we can effectively keep track of everything going on with the water quality. And the mission will have a joint operation for the first year between the students and the communities. But after the first year, the mission operation will be mainly handled by the communities. So in order to verify some of the requirements and potentially assist elsewhere in the project, we had to do a few analyses. The lifetime analysis helped us verify that we can provide the minimum 2 years, because if the satellite, if the orbit and the satellite shape and things like that reduce the lifetime of the satellite below 2 years, we don't want to consider that because that's not going to meet the requirement. The facility access analysis was done to ensure that the orbits we selected can communicate with the facilities, no matter where in Canada the facilities are, and that they have regular and predictable intervals of access. And the solar panel area analysis was done to sort of assist with the power budget that will be showing up later, and select an ideal orbit that will maximize the amount of power we can generate over the course of the orbit. In order to perform these analyses, though, we have to determine viable orbits that will have launches that are within our budget, as well as facility locations to use in the analysis. I'll now be handing off to Noah, who will be covering these few topics.
Thank you, Ryan. Let me just make sure I have the remote access. Okay, there we go. Sorry, just trying to move the screen here.
It's a bit slow. No.
Okay. There we go. Okay. There are many launch options, with the key drivers being availability, cost, and coverage of Northern Canada. The key parameters to these launch options are inclination and local time of ascending nodes for sun-synchronous orbits. On the next slide, here are some visualizations of the launch parameters. On the left, you can see the inclination is the angle between the equatorial plane and the orbital plane. In the middle is a representation of sun synchronicity and their local times of ascending nodes. The local time of ascending node, or LTAN, is the local time at which the spacecraft crosses from the southern hemisphere to the northern. On the right is an example of a dawn-dusk orbit, because as you can see, when the craft crosses the equator, it is on the terminator line between night and day, and while it is ascending, it is morning or dawn, and as it descends on the other side of the planet, it is dusk. The potential orbits we plan to launch in are as follows: a sun-synchronous orbit with an inclination of about 97 degrees, an altitude of about 500 kilometers, and 3 possible LTANs. We have also considered the ISS orbit, with an altitude averaging much lower, around 420 kilometers, and a much lower inclination as well of about 51 degrees. One key point is that this deployment can only be achieved through certain launch providers. The high inclination of the SSO orbits allowed the satellite to access more northern latitudes, which is more desirable for providing the service to northern communities. Also, the SSO orbits have a much higher lifespan because of their altitudes. Here is a short video, let me just make sure it will play, showcasing the different orbits and the latitudes and longitudes that they will cover.
Otherwise, Haya, could you play it?
Yep. 1 second. Sorry, just 1 second.
You might need to put it in presentation mode again.
Need to try that. Is it playing?
No, afraid not.
Oh no. Okay.
Let's move on, and if we get the chance later on, we'll play the video of the orbits at the end. Okay.
Apologies for that.
Okay, thank you. Now, through research and references of previous missions, we have selected some potential launch providers with the ability to place our satellite to one of the previously proposed orbits. There are many options, again, with most having altitudes of 400 to 600 kilometers and varying inclinations and LTANs. Our craft would use their rideshare programs as it does not warrant a dedicated launch. The 5 we have chosen are Exolaunch, Spaceflight, Switch, Alba Orbital, NanoRacks, and ISI Space. Each of these has specific parameters and qualities that will be further investigated to determine the most suitable launch provider. This brings us to the facility locations. We have chose these facility locations based on water advisories and the density of native population. Each of these lay near a large water source that supplies the communities around it. These locations were chosen to be spread across different longitudes and latitudes that span the eastern, western, and northern parts of Canada to simulate the effects of different orbits on coverage. This way, our satellite will be put into an orbit that will have substantial coverage of Canada. We plan to allocate resources for 5 ground stations and 10 water sensors to be spread amongst the communities, so the current 3 ground stations are a representation for analysis purposes. Now I will hand it back off to Ryan.
So the first analysis we had to do was the lifetime analysis. The lifetime analysis was performed, is it switching? Oh, the lifetime analysis was performed to ensure that our requirement of a minimum 2-year lifespan is viable for various orbits. And it works by simulating the effect of atmospheric drag on the orbit of a satellite, assuming that the satellite lifetime ends after its altitude decreases past 100 kilometers. The drag would slow down the satellite as it orbits and decrease the radius of the decrease the altitude of the orbit until it eventually comes back into Earth's atmosphere. The simulation assumes that the satellites would be launched around June 2023. We selected 2023 as the simulation start year because of the increasing solar activity, which nearing a solar maximum in 2025 roughly. Solar activity can have a large effect on the density of the upper atmosphere, with high solar activity making it a lot more dense and increasing the drag on satellites. Our current solar cycle had its period of low solar activity a year or so ago, with the expected peak solar activity predicted to be in 2025, the solar maximum. As such, beginning propagation in 2023, expecting a minimum 2-year lifetime requirement would put the entire lifetime within an area of very high solar activity. And this will approximate a worst case scenario solar and atmospheric environment and cause the spacecraft to re-enter a lot quicker than it would during times of low solar activity. If a satellite can stay on orbit for 2 or more years in the environment that we're putting it in, then the orbit should be considered viable and meet the requirement that we had set out. In this environment, all sun-synchronous satellites had a lifetime of more than 3 years, with dawn, dusk, and mid-morning having 3.8 years, which is almost double what our minimum requirement is. The ISS orbit satellite had a lifetime of less than 1 year, which is half of what we want and should be considered non-viable because of that within the high solar activity. This is a visualization of the satellite lifetime using orbit apogee height or altitude, with the highest point, which is the highest point on a satellite's orbit around the Earth. As shown, the apogee height in the ISS orbit decreases extremely quickly, with all sun-synchronous orbits maintaining a steady altitude for significantly longer. 2 years being the minimum, it doesn't decrease by that much, which is exactly what we need. The next analysis we did was the facility access, or facility to satellite access. When performing these analyses, a constraint was placed on the axis to prevent access when an angle between the horizon line from the facilities to the satellite is 30 degrees or less. As you can see in the graph in the top right, or the diagram on the top right, from the horizon to the line connecting the facility to the satellite, that has the elevation. And the lower the elevation between a ground station and a satellite, the higher the slant range, which would decrease the power significantly of the antenna, which we don't want. So in order to constrain it so that we can ensure that the antenna will have strong enough power to transmit all the data without too much error, we constrain it to 30 degrees or more, up to 90 degrees, where the range will just be the satellite's altitude. The graph on the left, the low latitude facility access to satellites, shows the access from Keewatin, but also is representative of the Splats and Okanagan facility. And as you can see from this graph, all the satellites have access to these stations, but the ISS orbit has all of its accesses clustered together, while the sun synchronous orbits have them spread out throughout the day, with roughly 2 each day. On the right side is the high latitude facility access to the satellites, but only 3 of the 4 satellites have access, with the ISS orbit not being able to access a satellite or access the facility at this high of a latitude. Since the ISS orbit can't access it, again, should be considered non-viable for the requirements of the mission. If we look at the graph of all accesses clustered together, all accesses to any of the stations by each of the satellites, we can again see that the ISS accesses to the facilities are all clustered together, while the sun synchronous ones have them more spread apart, which could alleviate some access. If there are too many people trying to access it at once or too many things to downlink, we can spread them apart throughout the day and reduce the requirements on these systems. So the next analysis is the solar panel effective area analysis. So when we're trying to determine how much power we'll need to generate and store on orbit, a useful analysis to do is an analysis of the effective solar panel area over the course of one orbit. In this case, I have had it set from 1700 to 1830. And this will help us determine where we should place our solar panels to maximize power generation and how much power we might be able to generate. From the top left to the bottom right is the graph for the ISS orbit satellite, the mid-morning sun synchronous orbit, the noon-midnight sun synchronous orbit in the bottom left, and the dawn-dusk sun synchronous orbit on the bottom right, with the total effective area for each of the satellites being the blue line that appears above the other lines. This will give us an idea of how effective our solar panels will be at generating power over the course of one orbit, where we can potentially remove solar panels and move them elsewhere. And yeah, when the satellite is not in view of the sun at all, you'll notice a harsh drop or spike depending on what part of the orbit you're on. So for the first 3 graphs, top left, top right, and bottom left, you'll notice that it's 0 for for a decent chunk, and then it spikes up when it enters the sunlight again. As it progresses, it changes as different faces now have access to the sun, and then a sharp drop again as it moves back behind the Earth. The difference between those 3 graphs and the one for the dawn-dusk sun synchronous orbit is that the dawn-dusk orbit doesn't go into eclipse, it doesn't go behind the Earth, and therefore it always has access to the sun. So the red line you see on the dawn-dusk sun synchronous orbit, that's just flat, and below the line above it, which is the total. The red line is the side that faces the sun constantly throughout the entire orbit. That'll definitely give us consistent power generation over the course of the orbit. And for convenience in comparing these graphs, the dotted lines on the other 3 graphs are representations of that red line on the dawn-dusk graph. So other small differences between the three non-dawn dusk sun synchronous graphs are that the noon midnight graph, the one on the bottom left, has the highest variation in its total, but also has the highest spikes of individual solar panels. So the panels facing nadir or towards the Earth, and the panels pointing towards and away from the satellite's direction of motion, both rise significantly above those same panels on other orbits at their peak. So this will help us just determine where we need to put the satellite solar panels. For instance, if we have the dawn-dusk sun synchronous one, we only really need to put panels on the one side that will constantly face towards the sun, allowing us to maybe save cost and reduce the number of solar panels, or concentrate all the solar panels we need on that one face to maximize the power generation of that side. Next, I'll be passing it on to Alex for a quick talk about margins and contingencies.
Yeah, hi everyone. My name's Alex. I'm the program management lead. So a quick clarifying comment about terminology. Could we actually change the slide, please? I'm not going to take control just for one slide. Yes, so contingencies and margins. These are two terms that are often mixed up or used interchangeably, and that can lead to some confusion. So I just wanted to make sure we're all on the same page before we dive into engineering budgets, although this will also be relevant for financial budgets. So when we have a certain project, there's a certain resource that we need to allocate. It's expected that the need for that resource will grow as the project goes forward. This is true for all projects, and space missions are not immune from that. And we call that that planning for the anticipated growth of the resource, we call that contingency. And the planning for unanticipated growth, traditionally it's said it's unknown unknowns. It's things that are completely out of our brainstorming, any potential risk that might happen. That's saving for a rainy day, that's margins. So that's how we're going to differentiate between the two. Traditionally, known, unknown, contingency, unknown, unknown, margin. That's all. Thank you. Ryan, you can keep going.
Thanks. On to someone from systems.
Yeah, hi. So my name is Pedro. I'm from the systems team. I'm going to go over the budgets for the mission. So we're going to start over here with space segment, the power expenditure for the CubeSat. So here, the components that will be using power are listed along with their nominal usage in watts. The nominal usage considers contingencies and duty cycles, which are defined in here as well. Contingencies were roughly based on their technology readiness levels, or TRLs, which basically is a measure of how ready they are for flight, or how much history they have behind them, how trustworthy they are. So components that have flight heritage have lower contingencies than those with no known flight heritage. And duty cycles for all budgets were based on a sun synchronous dawn-dusk orbit. Nominal usage here is the raw number for their power expenditures. For peak values, 100% was assumed for duty cycles, as this would be the worst case scenario. Okay, so for the space segment power generation, again, the CubeSat. For the power generation on the CubeSat, the EnduroSat EPS was picked, or energy power system. It includes 20.4 watt-hour power storage capabilities, which, if the CubeSat were to be launched with a fully charged EPS, which we assume to be the case, would provide energy to the system, which is why it's in this slide. For contingencies, the numbers were again roughly based on TRLs, or technology readiness levels. For the ISIS solar panels, the contingency was doubled to account for any extra costs incurred by adaptation and integration, considering the fact that the EPS is to be provided by EnduroSat, which is a different manufacturer than to ISIS. Nominal duty cycles here labeled duty cycle are 100% for the dawn-dusk orbit mentioned earlier. Worst case duty cycles in our calculations served as an emulator for any errors or issues that might arise in the mission. And so because of this, the duty cycle for the ISIS solar panels is lower than 100%. All totals here labeled surplus power are calculated using the respective expenditures, which are featured on the previous slide. And next we have the ground segment power budget for the sensor suite. So for the ground suite, the following sensors were considered. Their nominal usages were calculated. In cases where actual amperage could not be discerned, an amp expenditure of about 0.015 amps was assumed. Contingencies were also roughly based on TRLs, like before. Duty cycles for these components were based on their ease of use and their ubiquity in data testing, or like water quality testing. Most duty cycles don't exceed the 50% mark, primarily because of winter months and other possible considerations that might limit their use. And for the peak duty cycles, the nominal duty cycles were roughly inflated using the same rationale that was used in defining the initial ones. And here we have the space segment mass budget for the CubeSat. So for the CubeSat mass budget, most major components were considered. Contingencies were, again, based on TRLs. For the filters and amplifiers, there was no known flight heritage, which is the big products we found. The contingencies were therefore inflated accordingly. Their total masses for all the parts, including contingencies, are also listed here. With a 20% margin on the entire mass budget, a total of about 1.3 kilograms was arrived at. That's it for the budgets. So I'm going to hand it over to Amal for the engineering budget links. Sorry, this is the first few budgets.
Thank you, Pedro. So my name is Amal Dev. So I'll be presenting the link budget. So coming to the link budget, we have two different communications architecture, one for the telemetry tracking and command, and the other one for the payload, which includes the primary and the secondary payloads, also known as the water quality sensors and the SMS system. The reason we have two architectures is because of the restrictions on the usage of amateur radio bands without an operator, and this implies that the sensor suite cannot be designed to use amateur radio bands. Therefore, we choose the LoRa band for the sensor suite, which is a well-suited and actively used in Internet of Things, which our framework is based on. Some of the assumptions we use for the link budget estimation are that the orbit is at an altitude of 474 kilometers and the elevation angle is 5 degrees. So our goal is to find the minimum elevation angle at which the link closes. So for the ground station, we have a helical 8-tone antenna. So that's on the right side, and transmitting at 437 megahertz. For the spacecraft, we have an Omni antenna at the same frequency. Both are circularly polarized. This is to reduce the cross polarization losses. For the sensor suite, we have a 915 megahertz patch antenna, and the spacecraft has an Omni antenna at the same frequency. Again, both are circularly polarized to reduce the cross polarization loss. So based on the assumptions we just discussed, we have a closed link for the tracking, telemetry, and command with a link margin of 7.9 dB for the command signal. That is the signal sent from the ground station. And this is calculated using the signal to noise ratio method. We are using the values from the signal to noise ratio method because it's more conservative. And we have a 5.9 dB margin for the downlink on the other hand. On the other hand, the link does not close for the primary and the secondary payload. We have negative 6.8 dB for the command, which is for sending the data from the sensor, and a negative 10 dB for the downlink. And this is primarily due to the shortage of available power. In short, we tried different elevation angle for the payload architecture and found out that the link closes at an approximate angle of 40 degrees. So that is those margins are shown at the bottom. And we can always close the link at a higher elevation angle, but this reduces the available time for sending and receiving the information. So at an elevation angle of 40 degrees, we have a link margin of 4 dB for the command. So that is sending the data from the sensor suite to the spacecraft, and a link margin of 0.8 dB and for sending the data from the spacecraft to the ground station. Now we are on to the question, is our mission viable? The analysis performed and calculated budgets lead us to believe that this mission is viable. Now I will pass it over to the systems team.
Yes. Thank you. Perfect. So hello, everybody. We're the systems team. And in this section, we will be speaking about the design of the CubeSat as well as the ground station. So as we were designing it, there were many components that we had to keep in mind, like the power generation, the storage, communicating back to the ground station, the wiring and electrical components, as well as the onboard computer that we're using to process all of this data. Our team consists of 4 members: Pedro, who you've already heard from while he was doing the power and mass budgets, as well as Tim and Stephen, who you will hear from in a couple of minutes while they do the system block diagram. And the final member is myself. My name is Haya, and I am the systems team lead. So here we have some of the key system requirements that the team has set as indicators of the mission's success. We planned our components keeping in mind that these are our goal objectives. So beginning with ground segment lifetime of 3 years, and this includes 1 year for the design as well as 2 years for the actual mission. Next, we want our CubeSat's telemetry tracking and command, as well as the water data, to be transmitted in the amateur satellite frequency range. The next requirement states that our design must be able to operate in the environment in space. So the chosen components must be able to handle temperatures between -103 to +96 degrees Celsius, as well as magnetic fields of up to 100 microteslas. Another key requirement for the system is the ability to send encrypted messages from any SMS-enabled device in the mobile frequency range. The next requirement targets our primary payload with the aim of testing water quality by sampling contaminants such as ammonia, dissolved oxygen, pH, chloride, chlorophyll, conductivity, and water levels, and tests them against standards set for drinking water in Canada. Finally, it's essential to ensure that we meet the launch provider's requirements, meaning that our satellites will be compliant with the requirements that are specified in their interface control documents. We will also be taking margins into account to ensure that any slight variations are accounted for. So at this point in the mission design, it's not our goal to capture the detailed design of all the systems just yet. So this slide captures the conceptual designs of the systems that will drive mission success. The critical systems of the water mission in this regard are threefold. First is the ground-based water sensor suite, as well as the sensor management and the communication system that are required to monitor multiple aspects of water quality in different locations during all seasons. So the exact location for sensing will be finalized in the preliminary and detailed design phases of missions a little bit later. But early research has shown that there's value in measuring water sources both in the communities directly and the water sources for the wildlife that may be feeding back into the community. This means that our research will extend from water tanks and tap water to riverways, streams, and lakes. Second is the communication system between ground sensors and the satellite, from a low-power ground-based system to a low-power space segment. And this is because one of the main challenges of ground infrastructure in northern communities is the extreme weather. And because of that, each of the sensor suite sites may still benefit from data reporting via the satellite rather than through just a local wired or wireless network. Most of the sensor suites would require their own power source, suitable for all seasons, as well as health reporting capabilities and the potential for remote software updates. It's also incredibly important to design with ease of maintenance in mind, which leads us into the third system driver, which is the telecommand and telemetry station, as well as the payload data processing chain, which needs to be designed for ease of use by the community operators and provides data suitable for community allocations. The space-to-ground communications for sensors in the community SMS devices are challenging due to the difficulties of closing the RF link for low-power devices on both space and the ground ends. Therefore, the point design has assumed LoRa transceivers, which are short for long-range transceivers for both the payload sensor suite transmissions and the SMS devices. I'll now be passing it over to Tim, who will be talking us through the system level block diagrams.
This and following pages will show the system level block diagrams, which describe the layout of the various segments. Looking at the legend, red arrows show the flow of power, blue represent command and control, any signal that changes the behavior of a component. Black arrows show the water and SMS data. Gray arrows represent downlink, green uplink. This block diagram provides a breakdown of the ground sensor system level components and their role in the system. The power subsystem for the ground sensors utilizes wind turbines, rechargeable batteries, solar cells, and a solar LiPo charger, which charges lithium polymer batteries. In addition to this, various sensors have been selected to perform measurements and water quality analysis. The sensors are grouped into 3 subgroups: sensors that must be in contact with the water, sensors which must sample the water internally, and sensors which do not need to be in direct contact. The power and sensors will be controlled by an Arduino Edge microcontroller. This sensor data and status will then be sent to the satellite via the LoRa long-range modulation technique transceiver at 915 megahertz. The telemetry tracking and command ground station is powered either by community mains power when possible, or by a renewable energy production module otherwise. The station transmits and receives in the amateur satellite ultra-high frequency range. All command and data handling is done using a group of Arduino microcontrollers and Raspberry Pi single board computers. The Pis can then connect to a community computer, allowing a community member to read data and send commands to the space segment. The design is intended to focus on low-cost components with easy interfaces and ease of replacement, to allow a large number of community members to be able to interact with the key devices and learn how to use, replace, and upgrade said devices. The CubeSat system will be interfacing with the community members' phones and with the communication systems of the ground sensors and ground stations. The spacecraft design is quite simple with no attitude control, using omnidirectional antennas. The principal components, therefore, simply consist of the power, onboard computer, and space-to-ground communication systems for TT&C and the LoRa communication systems for the payload communication. However, it is assumed that some filtering and amplification may be required for these communication systems. The communication subsystem was also broken down into payload comms and operational comms to differentiate the two in terms of criticality and their ties to mission success. LoRa communication to phones and sensors will utilize a deployable antenna system from the manufacturer ISIS, and communication to the TT&C station will use an ultra-high frequency antenna 3 from Endurosat. The power subsystem consists simply of ISIS solar panels and an Endurosat electrical power system. I will now hand it off to Stephen.
Hi, I'm Stephen. The SMS service is designed to help people of the communities receive or send important information as need be. For the design, we use the same transceiver and antenna as the sensor suite. This is to keep the frequency requirements to a minimum. Using the same frequency as the sensor suite means we don't need a third transceiver in the CubeSat, saving space and money. These will both communicate at 915 megahertz. For communications and power, however, we will allow the communities to plug their phone directly into the transceiver. This will be done based on what cord the community needs for what phones they have. Once the phone is connected, it will then be able to power the system. As for communications, we would then be able to use the phone's keyboard and possibly an app to send the data needed as well as receive any incoming data. This will allow our communities to communicate not just with us, but other communities as well, and hopefully adds an easy way for everyone to keep in touch. Also, while designing all this, we will not obviously have the most efficient or proper system for every part during these early stages. We as a group have realized that another option that might work better would be designing the sensor suite to use the same frequency as the phones themselves, using 700 megahertz. This would cut the need to have a transceiver and antenna for the phone to plug into, allowing the phone to use its own transceiver and antenna to send and receive the data. However, this comes with its own problems with interference and other things. Summary. For the mission objectives, what goals are we planning to achieve? First and foremost, we wanted to know exactly what we were working towards. We We want to be able to sense the water qualities in areas that don't get the best water treatment, especially Indigenous communities. We wanted to design a CubeSat so we can monitor a wide range of places in Canada and get this information to everyone without having to physically be at each site. We wanted to see if this would be feasible in a 4-year engineering program. The mission objectives then helped us design the requirements needed. These helped us define the most important parts of our system, understanding exactly what is needed to sense proper water, how we plan to transport this data to the communities who needed it, as well as the finer details on how they would work, which was crucial to figure out early on in order to help design the systems properly with everything in mind. Using these requirements, we were then able to figure out the drivers of our mission and roughly how they would interact with each other, as well as start to pick parts. Through the requirements, we knew that we needed a CubeSat to receive and transmit data, sensor suites to test variables in the water and send the data, ground stations to receive and store the data, and as well as an SMS system to keep the communities informed. Now that we knew everything we needed to achieve our objectives, we could then start to properly design each system and make sure they could all interact with each other. Finally, once we had everything figured out, all the parts picked, and had everything interacting together properly, we wanted to finalize it by creating a system level block diagram that properly shows how it all works. This helped us flesh out any mistakes that were hard to see just through the documents alone. For example, one of the transceivers we picked for the ground station was able to transmit the data at the frequency the CubeSat would receive. However, it didn't receive the frequency the CubeSat would transmit. This is an oversight we didn't notice until we mapped it all out on the system level block diagram. Finally, the feasibility of it all. Looking back at everything we designed, we believe this would be a totally feasible mission from a systems team point of view. The power generation is greater than the power consumption, meaning the power budget is attainable. The mass and volume is less than the requirements from launch vehicles, meaning the mass is viable. Everything works in the same frequency ranges as well, which means frequencies are feasible. All is designed within our monetary budget as well, so prices are achievable. All our components are also compatible, so the designs are realistic. And overall, we did plenty of research to make this mission as feasible as possible and believe this is an achievable goal from a systems point of view.
Hi, everyone. Alex again. The next section we are going to cover is program management. Oh, I'm so sorry. I took control way too quickly. Do we have any questions?
Perfect, Alex. So yeah, so we've been through impact communications, we've been through mission systems design. Before we go through program management, we thought it would be good to take a chance here for any questions on the mission concept, the systems design. So any questions from anybody? We'll give it just a minute longer. And if not, we will push through to the end, and then we'll have time at the end for bigger discussion. So no questions, then carry on, Alex.
All right. Well, as you can see, I was just so excited about program management. I couldn't contain myself. So the super exciting stuff we're going to talk about is how we are going to do all this work in the context of a 4-year program. So what does the work look? How does it break down? How do we fit it in a schedule? How do we manage cost and risk? We're all going to cover that in this section. But for the time being, I'm going to hand it off to Mohammed, who will get you started on the schedule. You are muted, Mohammed, if you're trying to speak.
Yeah, for some reason, I had no idea how to unmute myself while I was taking control. So yeah, sorry about that. I'm gonna share my screen in a second now. Okay, so I hope you guys all can see the PowerPoint.
Yes, we can.
Okay, awesome. So yeah, my name is Mohammed. I'm part of the program management team. I would like to say first, hello, everybody. Thank you for taking the time to be here today. In order to envision our 160-week program, we looked what's it going to look like. We had to examine the traditional way of building a space mission and how it will fit in the 160-week program we are trying to build, which will lead us to the NASA mission design phase, the traditional NASA mission design phase. As you might have seen, NASA mission design phase is a traditional blueprint to any space mission. Consists of 5 phases. Every phase demonstrates a major step in completing a space mission. So we have phase 1 over here, which is like preliminary analysis. Phase B is definition, and will also display how that will fit into our 160-week program as well. As we can see, the first 2 phases will be able to fit in the first year. Third phase, design and development, that's going to have its own year, second year. Also, phase D, which is testing, that's going to be third year. And the last 2 phases is going to be for operation, and that's going to have its own year after the program ends on the third year. For our mission, we wanted to have community engagement and impact of the mission at the forefront of our mission design. So what we did is to truly reflect our vision, we redefined the mission design phase to focus heavily on the community input and impact on those communities as well. So as you guys can see, this is the traditional NASA mission phases. And this is how we envision the mission phases is going to look like. So that's going to be communication, communication establishment, relationship building, transparency, trust building, and training collaboration. As you guys can see, the first 2 phases are going to fit in nicely in the first year. Second year, that's going to be training and collaboration. Phase D in the traditional NASA phase, that's going to be sharing, which will include testing, which will be in the third year. And then the last 2 phases, that's going to be the handoff, which is the operation year, which will be the 4th year. Moving along, for all of this to make sense, we will take a look at the higher level work breakdown structure, just to be able to get a sense of how that will look like. So as a start, we'll start with program management. We found out that the program management, it's better for team member to share the project management role and tasks, which will be like different task costs, schedule, risk, and we also find it nicely that they will also track learning and community impact as well. On the first year, as we have seen earlier, we have the first 2 phases, and we here outline some of the tasks they will be doing, like community connections, finalizing requirements, community engagement, mission system analysis, and trade study, among the rest. And also we have on the second year, we have the training collaboration, which is design finalization, finding on the suitable parts, and planning the testing that will take place on the third year, which will include testing, assembly, and community training and involvement. The 4th year, as I have been mentioned before, that's going to be the operation and the community handoff, and any other learned lessons. Moving on to an example, a lower level detail example of the WBS. Here we're going to look at one of the phases that we have, transparency, trust building phase. As we can see here, this is an example of different teams that will be working on this phase. So we have program management, mission team, system team, impact. And as we can see here, we're able to provide examples of what are the things that they might be doing during that phase. One of them, a cost estimate, student training, communication with communities. For mission team, that's going to be a requirement, engineering budget, mission analysis. System team will include the system segment team and ground segment team, which include some of the following: structure, ground software, power and SMS communication system, and water sensors. Impact team during that phase will be doing impact tools and impact processes. And moving along. So here we're gonna take a look at the student journey and how that will look like throughout the 160-week, and what kind of areas they can gain knowledge on. One of the areas they can we are looking at so students can spend a minimum of 6 weeks in each of the following areas. So not just these areas. We still have other areas student can spend and gain knowledge from. Electrical, mechanical, on top of that, of course, program management, communication, and mission and impact. And if they spend more than 50 weeks, they can get the specialization in that area. And we're showing some of the work breakdown structure, and the highlighted rectangles over here in red that shows a student who chose different areas to work on during the mission. And then moving along, we're gonna display how the year will look like, a sample year during the 160-week program. So it's gonna have the traditional thing, fall and winter, each one is 14 weeks. It's still gonna have the normal normal winter breaks and summer breaks. And in our program, it will include the summer as well. So we have S1 and S2. And just because of how the nature of the program, since it's based on a project, not really courses, so we can able to fit nicely in the middle 8 weeks of summer vacation. And before they start the next year, that's gonna be 1 week fall break. And yeah, that's it for me now. And I'm gonna pass it to Yusuf, I believe.
Yes. Hey everyone, my name is Yusuf. I'm also part of the program management team. So before we dive into the figures for the financial budget, just a couple of notes to keep in mind so that we can better understand these figures. The contingency is based on NASA's Green Book. So this basically entails the contingency cost factor with respect to the design maturity, and design maturity is based off of flight heritage, space grade, and non-space grade parts. And at this conceptual phase of the mission, all the margins are estimated to be 20%. This is just a standard. And yeah, so next slide. Oh, am I in control? Or? Oh, okay.
I did move to the next slide. You can take control if you would like.
No, it's fine.
Okay, that's fine.
Okay, so moving on to the financial budget, we have the space segment. Here, most of the parts are the parts that have already been listed by the systems team, such as the spacecraft bus, transceiver, and other components. Oh, can you move to the next? There's an animation for each. Yeah, okay. So here, this is the rounded up figure that we have. The reason why we have such a high maximum expected cost is because we have a filtering PCB system that's that we're going to be building in-house, and there's some parts that might not be completely space grade materials, which is why we have the cost we have over here. Next, to go over the ground segment, it's divided into 3 parts, which is the ground sensors, ground payloads, and the other ground components. So for the ground sensors, we're going to have a total of 10 sensor suites because we're going to plan on reaching out to 5 communities, and each of those communities is going to have 2 sensor suites to detect the water, water level, and other such things. So this is the costs that we have estimated for the ground sensors. For the ground payloads, this is, as was mentioned earlier, in regards to the payloads with SMS or short message service, as well as telemetry and command towards the Cube satellite. There's going to be, like I mentioned, 5 different communities that are going to have these payloads available. And the other ground components are in regards to the batteries, solar cells, and other components that will be helping the payload as well as the ground sensors in the ground station. Moving on, we have the launch providers training and outreach, and then we'll be looking into the total. For launch providers, we have a rough estimate or range between having an $85,000 launch to $125,000. It is possible that we could maybe alter this cost, as there in the university we have a Launch Canada initiative in which this will allow us to maybe launch our own our Cube satellite with the assistance of one of those launch vehicles. So this is something to consider later on. And then we have training and outreach. This training involves training the communities and allowing them to be able to use these ground stations to better understand how the data is being received and to access this water, clean water. Outreach also refers to supplies and whatever food or bonds we might need to make to create a bond between the communities we have. And yeah, and then we have the grand total for the overall mission, which is going to be around $266,000, and then we have it could be a maximum of $422,081. One thing to note is that all these costs are in USD, and yeah, I think I'm gonna pass it on to Alex now.
All right. So the next area of interest as far as program management is concerned, there we are, is risk management. So our plan follows a pretty traditional approach, and so it's comprised of the 3 next steps. We have identification, where we define the risk, monitoring, where we keep track of them as the project progresses, and mitigation strategies, so team members know what to do when a risk becomes active. The first step is to define mission and program risks. So upon identifying a potential risk, it is assigned a unique identifying number, and it is described along with its possible causes and consequences. All subteams will identify their specific risks and forward the results to their assigned project manager and system engineer, who will keep a master registry and directory. From there, we have all the information we need and the tools to track risks throughout the project. And you can see at the bottom of the slide, there's an example of risk that we will use throughout this section. So similarly to the identification process, the subteams will be tightly knit into the tracking process. Each of them should track their own low-level risks on an ongoing basis. So what have I done? Okay, Mohammed, I'm going to give that back to you because this is too small for me to see. Sorry about that, everyone. Okay, so as I was saying, the idea at this point is to have a bi-weekly informal risk review at the sub-team level. So where importance, dependency, severity, and probability will be updated. And in addition, risks that are no longer relevant can be retired and new ones can be added. So note that this is in addition to a formal risk review and assessment. So it's not replacing the more formal, gate decision points throughout the project. Should a risk become moderate instead of low, it should be brought up to the project managers and systems engineers so that a contingency strategy can be outlined. I said contingency, I meant mitigation. So to quantify this process, we're going to use traditional risk matrix, probability versus severity, and the product of the two gives the risk factor, which will define whether a risk needs a mitigation strategy. Anything above 10 on this scale of 25, we're going to need a strategy. Can I have the next slide, please? Thank you. So this matrix here illustrates the current state of our mission risks. In it are a little more than a dozen key risks, 16 to be exact. And as is expected during this phase of design, they're all unlikely and pretty severe. So they populate the lower left corner of the table. Note that our example risk, number 16, is deemed possible and sorry, I'm missing myself. Our example risk is 16, and it is likely and moderate. So 4 times 3 is 12. That's above 10. That means it merits a mitigation strategy, which we'll see on the next slide. So there are 3 components to our mitigation strategy: a trigger state, an approach style, and the action to be taken. So in this example, the risk becomes active once the total power calculation exceeds the budgets, including margins, during the preliminary design review. The approach will be mitigation, and the action is going to review the power needs versus wants, reconsider the allocations we've done, and seek alternative to the parts we have selected. Can I see the next slide, please? So here are a few examples of mission risks. The top one is from impact, which would be that the community is not agreeable with our goal. This is actually a really big problem because if they're not on board with what we're doing, well, the entire mission purpose goes out the window. So we need to make sure that we don't get there. The second one would be from system, which is a failure to transmit a high priority message. Again, in a life or death situation, this is unacceptable. We need to have a mitigation, ideally a prevention strategy for this. 15 is from communications, which is that promises made cannot be kept. Again, it's kind of in the same line as one. Losing trust, which is already pretty shaky, would be pretty catastrophic to our relations and to the purpose of the mission. And so it's important that we keep that in mind and keep the risks, the systemic risks in mind, as with a traditional project, but also put the impact and the communication risks just as much as to the forefront as the more engineering related risks. So in summary, we've shown that the novel impact reflective mission phases are likely to be feasible with a 4-year academic calendar, that the program and the mission are financially feasible as well, and that we have a risk management strategy in place to tackle challenges that come with a traditional space mission, but also with the little twist that we're adding to the recipe here. So I'll pass it off to Celeste for the next section.
Okay, so y'all get to listen to me one last time. So we're almost at the finish line, so just hold on for a little while longer. Let me just jump into this. Naturally, like the last 2 times, you'd think I'd get used to this and be able to figure out how to work the slides, but I have not. There we go. So in doing our study, we found that our mission could work. We could work alongside the communities and have them drive the mission. And we strive to have transparency throughout the mission. That would be open communication, continuously posting and publishing any of our work on our website or on our social medias for anybody and everybody to access. There will be open feedback platforms for anybody to come in, make a comment if they feel that they need to. We expressed how our system should work and how this can be implemented into the 4-year undergraduate degree. Shows how it is feasible with cost and management and even the launch periods, how this could work. So overall, we believe that this mission concept could be implemented. And there is a chance for this to run through. And so our next steps, that would be in our 6th week of this pilot program, which is our following week, starting on Monday. We will aim to define the program in more detail. This will cover the sub-teams' roles and timelines, the recruiting process, as well as look into the educational aspect. So we believe that in order to have a program like this to work, we need many different students from a range of backgrounds to bring their different experiences to the table. And we want to be able to explore all these paths and opportunities that these students have available to us. So in terms of the education, this will open up a conversation in ensuring that our program would be accredited. So we need to follow the standards that are given by the Ontario Accreditation Board, and we need to see which skills and tools and classes the students need to know in order to meet these standards. So that's what we will be doing next week, and we will also be adjusting based on the feedback we receive. So right now, I think we should take a short break. And Franz, do you have a good time? Do you think we could jump back in at?
So it's 2:42. If we took a break until 2:55, that gives people a chance to go stretch their legs, grab a quick drink, and we'll kick off with the feedback, questions, comments at 2:55, if that works for everybody. And just to let you know, we will stop the YouTube stream before we get to the question and comment section so that you feel more comfortable. If you're worried about sharing that on the YouTube, we will be stopping the YouTube stream before we get to the feedback session. But anybody watching on YouTube, we will be capturing our responses to any feedback in a final update of our documentation in next week's activities. So great. So let's take a break till 2:55, and we'll pick up with the questions and comments then.